So, students, let me start with an introduction of the new topics in modern physics, and I would like to start with the concept of quantum radiation. So, to discuss this thing, we have the quantum theory of radiation, and it was proposed by Max Planck. And and the intuition of this theory was to explain the distribution of energy with wavelength in a black body radiation. And what he did, he actually put forward a hypothesis. And what was this hypothesis? This hypothesis was basically the atomic, atomicity of energy. And and he introduced what we call as quantum action, the concept of quantum action. I mean, this theory that Max Planck introduced, he was able to explain a number of phenomenon concerning the interaction of energy with matter. So you have energy and its interaction with matter. And what was the basic postulate was that was ascribed by Max Planck was that a linear oscillator, if we have an oscillator, it does not radiate energy continuously. It's a linear oscillator, right? Oscillator. It does not emit energies continuously, as is proposed in classical theory of electromagnetism. But what Max Planck proposed was that these linear oscillators does not radiate energy continuously as is required by electromagnetic theory of light. But the energy is emitted. It's emitted in the form of packets. Or we also call them quantas. Now, these oscillators, the oscillator emit energies only when it passes from some higher energy state to lower energy state. So these oscillators emit only when they pass from some higher energy state to the lower energy state and absorb energy when these oscillators have to go from the lower energy state to the higher energy state. So the emission of energy is based on a transition from higher energy to lower energy and vice versa. For one case, we have the emission of energy when the oscillator moves from higher energy state to the lower energy state, and in another case we have the absorption of energy. Now, another important thing here is that no emission or absorption of energy takes place when the oscillator is in some given state. So this is the most important point. So if there is some given state where it does not go for any state of transition, whether from higher energy to lower energy, then this oscillator is not going to emit or absorb. It means that it's neither emitting at that state nor is it absorbing. And the smallest energy which can be emitted. Now here we have here we have a fixing, right? So what's that? That fixing is that the smallest amount of energy which can be emitted or absorbed by this linear harmonic oscillator is given by h nu. As we understand, this h is the Planck's constant, and this nu is the frequency. It's the frequency of the radiation that's either absorbed or that's emitted. And the value of this Planck's constant is it is 6.62 into 10 to the power of minus 34 joule second. And we can also write its value in terms of erg seconds. And in ergs, its value is 6.62 into 10 to the power of minus 27 erg per second. So we have been traveling from the basic concept of atomicity of energy, and then a state of quantum action, then the interaction between energy and matter, and the possibility of emission of energy only when there is a transition from some higher energy state to some lower energy state. So this quantum, what we are talking here is h nu. It's the smallest possible quantum of energy. This quantum of energy cannot be divided. That's an important point. Cannot be divided. And this quantum of energy, which cannot be divided, we call this thing as photon. All right, the case should be clear up to now. Now, this theory has been able to explain a number of phenomena, as I said before. And what we have is it's able to explain a number of phenomena, right? And that could not be explained by classical theory. Classical concepts, the classical way of understanding those phenomena relating to the radiation. Now, if I take, for the sake of art, for example, if I say it gives us a satisfactory explanation of specific heats. Specific heats. This is the first important point that I can point out here. And specific heat of what? Specific heat of solids. When there is a variation of temperature. Variation of temperature. And these postulates are able to explain us the phenomenon like photoelectric effect. Photoelectric effect. Compton effect. And the specific heats of the solids, where when we use the classical approach like Dulong-Petit's law to explain the specific heat of solids, it fails to explain us the variation in the temperature, variation in the specific heat with respect to the temperature. Whether we take the variation in the positive direction of temperature with respect to the degree Celsius, or to the negative direction of the temperature with respect to the 0 degree Celsius. So this specific heat problem, it gets us satisfactory answers in the postulates of Planck's in the postulates that were given by Max Planck, and photoelectric effect, which was basically explained by Einstein by using the postulate of Max Planck, He could perfectly explain a photoelectric effect, and this led him to have Nobel Prize in physics. And similarly, Compton effect. This Compton effect could also be explained by virtue of assuming that the radiation that we have has it's in the form of quantas, and that quanta is called as photon. The thing that I explained before, the minimum energy this oscillator can absorb is called as photon, and that energy is h nu. Now, this photon, if we talk about this photon, it has frequency and it has wavelength, and we know the relation between frequency and wavelength as nu is c by lambda. This nu is it is the frequency of radiation. It's the frequency of radiation, and this lambda is the wavelength. Is the wavelength of the radiation. So if I substitute this in the upper equation, then the energy of this photon can be written in terms of wavelength, that is hc by lambda. Right? Now, if we move on from here, if I call this as equation 1, right now, we have, according to the theory of special relativity, we have the well-known relation between energy and mass. And what's that relation? That relation is E is equal to mc squared. Now, in this equation, what is m, what is c, and what is E? E is the energy, m is the mass. In actuality, it's the mass defect. Now, c is the speed of light. So here we have a correlation where we can have conversion of energy into mass and conversion of mass into energy. So from this equation, if I have to write what is mass, mass is E by c squared, right? So this is the mass. Now, in the original equation, what I have is I have E equals hc by lambda, right? And if I make use of this E in this equation, right? So what am I going to get here is this is equal to so substituting for E that's there. So if I substitute 1 in 2, what am I going to get is this m is this is hc by lambda c square, right? So here we will have the cancellation square, and this will cancel, and this lambda can be taken up, so lambda is h by mc, right? Now this is my wavelength of the photon, right? And I can also write the momentum for this photon. So what will be the momentum for this photon? If I choose this c as the velocity, so in that case I can see that this mc is h by lambda. Now this is p is equal to h by lambda. So what I have here is the momentum of the photon, right? And lambda is the wavelength of this radiation, which is considered to be the quantum of energy in view of Max Planck. Now, in order to move on from here, I mean, this photon that we are talking about, it's a particle of zero rest mass. So it has zero rest mass. it means, in other words, that a photon can never stop, because when it stops, it doesn't have any mass, right? And it has the dynamical variables uh, associated with it in the form of energy, and this energy is h nu, and in the form of momentum. So energy and momentum are associated as the dynamical variables. So the case is clear here. So for momentum, it is h by lambda, and for energy, we have Planck's constant times frequency. Now, this photon has zero charge. It does not have any charge. It has zero charge, and it has spin equal to 1. That's why we say it has an integral spin. So it has spin equal to 1, right? And the unit that we have, suppose we say h is the Planck's constant. We introduce h bar as h by 2 pi, well, using it in certain problems, in certain situations where we have to derive certain equations to explain certain phenomena. Now, if we talk about two charges or two magnets, say for example. Now we have two charges. Between the charges, there are electromagnetic force. There are electrostatic forces. There are magnetic forces, and these forces. When we think in terms of classical theory, there is a continuum of interaction between these forces. But what happens here, that when we have two charges, right? Or we have two magnetic poles or magnetic poles. Now, the force that's being there between these two charges, or the force that's being exerted between these magnetic poles, these forces are quantum in nature. I mean, there is exchange of photons. There is exchange of photons. When we make use of the quantum theory on the interaction between the charges, or the interaction between the poles of a magnet, there is exchange of the photons that leads to the force of attraction or the force of repulsion. Now, a photon can interact. It can interact with all charged particles, and can also interact with some neutral particles. It can interact with neutrons. Because of its particle nature. So, if I choose, and if I go with the choice, say for example. Moving on with the concept of photons is that a photon behaves as an elastic ball. It behaves like an elastic ball. For all purposes, I mean, when a photon collides with an electron, both energy and the momentum are conserved, as in the case of collisions between two elastic spheres that we have. You have a collision if it's a photon and we have an electron. Now this photon is chosen as an elastic ball, and this elastic ball interacts with the electron, and in this process, if we have To assume an elastic kind of scattering, what happens? The energy and momentum remains conserved in the similar way as we discuss the two particles in terms of the elastic collisions that we have. So, 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 so this fact has been basically verified experimentally by Compton in his experiment on X-rays. And when X-rays of frequency, say nu, when these X-rays collide with electrons, right? So what happens? We have the energy of the photon. It is the kinetic energy and h nu dash. So what's happening here is that we have the interaction between photon and electron, and this photon can be treated as an elastic ball. And the laws of classical physics that are valid for the solid balls are equally valid here. To have the interaction between photon and electron, and it was Compton who performed an experiment based on X-rays and obtained a relation between photon h nu and the formation of some kinetic energy and having some energy associated with the electron. So in this equation, what we have is we have the v, that's the velocity with which the electron moves, okay, and this nu dash is the frequency of the new radiation given out. And there is an interaction between electron and photon. You have the exchange of energy, and you have the outcome radiation, and the energy of that radiation is different from that of the original radiation that hits this electron. And this was experimentally put forward by Compton. Now, to move on in the same way, if I go with, suppose we have, what should I call as, I have a photon, right? I have a photon, and this photon has an energy equal to, say, 75 electron volts. And I want to calculate the wavelength of this photon, and I want to calculate the frequency of this photon. Now, in order to do that, we have the equation E equals h nu. Right? So from this equation, we can calculate nu is E by h. Now, what is E in my case? It is 75 electron volts. And we can convert electron volts into joules by multiplying it by 1.6 into 10 to the power of minus 19. Divide by the value of Planck's constant we have, approximately 6.6 into 10 to the power of minus 34 joule second. And in the numerator, we have joules. This joules and joules will go. So we will have the frequency because we are getting 1 by S. And this value nearly comes out to be 18.12, 1 by second. So this is 18.12 hertz. So this will be the frequency. This will be the approximate frequency of the photon that has the energy equal to 75 electron volts. And at the same time, we can calculate its wavelength, and we know that this nu is c by lambda. So that implies this lambda will be c by nu. So lambda is going to be speed of light. It's 3 into 10 raised to the power 8 meter per second. The frequency we have calculated is nearly 18.12. So take it only 18 into 18, take it nearly 18. So this is 3 ones, this is 3 6. So this wavelength is 1 by 6 times 10 to the power of, I have, just 10 to the power of minus 34, and this is 10 to the power of, I have missed this number, so this is here 10 to the power of minus 15 hertz, sorry, plus 15 hertz. All right, so this is the frequency. So here we can use 18 into 10 to the power of 15. Okay, so here we have 10 to the power of 8 divided by 10 to the power of 15. So we can see here we will have lambda nearly equal to 1.6 into 10 to the power of minus 8 meters. So this should be our wavelength of this, the wavelength of the wave that's associated, the wavelength of this photon that I'm talking about. So we have calculated the frequency and we have calculated the wavelength of this photon. Now, if I choose another thing, like I want to find the energy of the photon. So I want to find the energy of the photon, right? And what I am given is, and this energy of the photon is equal to momentum of electron, whose energy is 2 electron volts. Okay, so what am I supposed to calculate here is I want to calculate the energy of the photon, whose energy is equal to the momentum of the electron, which is equal to 2 electron volts. So for this, what I would like to calculate is the energy of the electron. So energy of electron. So what will be the energy of electron? That will be 1/2 of mv squared. Now, as per the given condition, this 1/2 of mv squared is equal to 2 electron volts, right? So we can think of mv squared is equal to 4 electron volts. That seems to be right. So I can write m squared v squared equals m4 ev. Now this m squared v squared is what? This is the square of the momentum of the electron. So this is p squared is 4m electron volt. And we better understand what is the mass of the electron. We have its value, and what is that? That's 9.1 into 10 to the power of minus 31 kilograms. And we can think of converting this electron volt also. And what will be my P here? So that is under root of 4m electron volts. Okay, that's the case. Now let's talk about the momentum of the photon. Now we have the photon, and in case of photon, what I have is, okay, we have got what? We have got the momentum of the electron. And what is the momentum of the photon? So momentum of photon, it is equal to what? P is equal to h by lambda, right? So here we can write for this momentum as P is h. So I have E equals h nu. So h is E by nu. So if this is the case, I can use this h here. So this is E by nu lambda. So P will be E by, so nu lambda is C. Right? So this will be the momentum of the photon. So momentum of the photon is what? It is E by C. Clear? So that should be the case, and we can also write the energy of the photon equal to E is equal to PC. Now, what am I interested to do here is this energy of the photon is equal to what? It is equal to this. It is equal to the momentum of the electron, right? The energy of this photon is equal to the momentum of this photon. So if I write this condition here, that the energy of electron is equal to energy of photon. Now, if that's the case, then what's going to happen here is that this E is equal to PC. Now, E will be equal to PC, right? Now, what is P here? P is this whole shit. This is under root of 2m times 1.6 into 10 to the power of minus 19 joules, and then you will multiply this with C. And when you will make the calculations, you will be able to calculate this energy of the photon, and this energy of the photon comes out to be nearly 14.3 into 10 to the power of 2 electron volts. So this is nearly 1430 electron volts. So this is how the small problems can be solved using the equations that are proposed there in the quantum theory of radiation. So with this, I would like to end this video.